that says that perhaps dark matter is nothing but matter, ordinary matter in another dimension hovering right above us.
Michio Kaku believes dark matter and dark energy are just two sides of the same cosmic coin. What if Euclid just found the flip? An invisible dark fluid that glues galaxies together and tears space apart. That's Michio Kaku's wildest cosmology bet. Today, ESA's Euclid has fired back its first map of 26 million galaxies, and the numbers are weird. Brand new gravity lenses, hidden mass exposed, even a hint that cosmic expansion might be slowing. Could Kaku's sci-fi fluid finally be real? Stay right here, because in the next few minutes, a bright progress bar to verdict already ticking, will test his boldest prediction against Euclid's fresh data. If the curve matches, cosmology gets rewritten tonight. And if it doesn't, we toss the theory into the void. Let's crack open the dark universe, the breakthrough that changed everything. On March 19th, 2025, astronomers basically got the cosmic version of a triple espresso. Euclid's very first data drop, just 3 narrow strips of sky, making up less than 0.5% of the full mission, delivered a jaw-dropping 26 million galaxies after only a week of exposure. Every pixel flew through Euclid's 2 high-tech eyes. VIS, a powerful 600 megapixel optical camera, and NISP, a near-infrared spectrometer. Working together, they tagged each galaxy's shape, color, and redshift, reaching back over 10.5 billion years into cosmic history. From that enormous haul, scientists built a detailed catalog of 380,000 galaxies, many classified by an AI assistant nicknamed Zubot, along with help from nearly 10,000 volunteer citizen scientists. This drop almost revealed 500 brand new strong gravitational lenses, including an Einstein ring wrapped around the spiral galaxy NGC 6505. It looks computer-generated, but it's 100% real, unfiltered universe. Euclid even spotted 70,000 globular clusters in the Perseus cluster and flagged possible supernova and fast radio bursts hiding in the frames. And keep in mind, all of this came from a sky area just 63 square degrees, about the size of 300 full moons laid side by side. The spacecraft is already beaming down over 100 gigabytes of data per day and has quietly mapped around 2,000 square degrees, about 14% of its full goal, as engineers continue dialing in the instruments. By 2030, Euclid will have expanded over 15,000 square degrees and log more than 1.5 billion galaxies. That's enough to create the first ever true 3D MRI scan of dark matter across the universe. No wonder one astronomer called the release an avalanche of discoveries, while another said it's a goldmine we'll be digging into for decades. And this was just the opening ripple. The real data tsunami lands in October 2026, when Euclid's next release will map 30 times more sky and take Michio Kaku's bold, dark fluid theory straight to trial. Let's talk about Kaku's dark fluid for a little. For years, Kaku has championed a daring idea that could flip our entire understanding of the universe on its head. He suggests that dark matter and dark energy, those mysterious forces that dominate 95% of the cosmos, aren't separate at all. Instead, they're two forms of a single, unified substance, something he calls dark fluid. In places where matter is packed tightly together, like inside galaxies or clusters of galaxies, this fluid thickens and behaves like dark matter, the invisible glue that keeps stars and galaxies from flying apart. But out in the vast, empty stretches of space, the same fluid spreads out, becoming more diffuse. And when it does, it starts pushing instead of pulling, generating a kind of negative pressure that drives the accelerated expansion of the universe, just like dark energy. It's a radical idea, but surprisingly intuitive. One ingredient, two behaviors, shaped entirely by the environment around it. Think of it like water. In cold conditions, it becomes solid ice. In heat, it turns to steam. Different forms, same molecule. In Kaku's vision, dark fluid acts the same way, morphing between gravitational pull and cosmic push, depending on the density of space. What makes this theory so powerful is its simplicity. It could answer some of the biggest questions in physics, like why the universe is expanding faster and how galaxies form, without needing two separate mystery ingredients. But here's the catch. So far, it's been just a theory. No telescope had the precision to put it to the test. That is, until now. With Euclid, for the first time, we have the tools to truly test Kaku's vision. By mapping how galaxies stretch and grow over billions of years, and by measuring how invisible mass bends light across space, Euclid could prove whether this dark fluid really exists, or reveal something even stranger. The universe is finally ready to answer the question Kaku has been asking for decades. What Euclid saw first? Thanks to Euclid, we now have the precision tools needed to truly challenge the secrets of the cosmos. At the heart of this mission are two powerful instruments working in perfect sync. First up, VIS, Euclid's 600 megapixel optical camera. It's designed to detect weak gravitational lensing, those tiny, almost invisible stretches and squashes in the shapes of galaxies. These subtle distortions are caused by massive, unseen objects, most likely dark matter, bending the path of light between those galaxies and us. Think of them as cosmic fingerprints, left behind by whatever's lurking in the dark. Then there's NISP, the near-infrared spectrometer and photometer. Its job? To measure something called redshift, how much a galaxy's light has been stretched as it travels across an expanding universe. By analyzing redshift, scientists can figure out exactly how far away a galaxy is and how far back in time we're looking. In other words, NISP lets us date the light from galaxies, turning the night sky into a three-dimensional time machine. When you combine the power of VIS and NISP, you don't just get a picture of where galaxies are, you get a layered, dynamic map of when they existed and how they evolved. It's like a cosmic CT scan that peels back the layers of space and time, stretching nearly 10 billion years into the past. No telescope has ever been able to stitch together the universe's structure across such a vast timescale with this level of detail and precision. Armed with this incredible cosmic toolkit, Euclid isn't just collecting pretty pictures, it's setting the stage for a scientific showdown. This is where Michio Kaku's dark fluid theory enters the spotlight to challenge the reigning heavyweight champion of cosmology, the lambda-cold dark matter model. LCDM has been our best explanation for the universe for over 2 decades, separating dark matter and dark energy into two distinct forces. But Kaku's theory challenges that split, and now, for the first time, we have the data to see which model holds up. Euclid is testing the growth rate of cosmic structures. Kaku's dark fluid predicts a smooth, continuous evolution of galaxy clumping from about 10 billion years ago to today. If galaxies formed and grouped in a steady rhythm over time, that's a point for the fluid. Euclid's ultra-precise maps can track how clustered galaxies are at different cosmic ages to check that pattern. Next up, the puffiness of dark matter, halos. In Kaku's dark fluid model, these invisible shells around galaxies should be warmer and more spread out than the dense, compact clumps predicted by cold, dark matter. Euclid's lensing data can zoom in on these structures and reveal which picture fits. And finally, dark energy over time. While LCDM sees it as a constant force accelerating the universe forever, Kaku's model says it was stronger in the past and is slowly fading. Euclid tests this using baryon acoustic oscillations, ancient ripples from the Big Bang, to trace how fast the universe has been expanding. A slowdown? That's a big win for the dark fluid. It didn't take long for the cosmic plot twists to begin. Just weeks into analyzing Euclid's first data, scientists spotted something strange, a hint that the universe's acceleration may have slowed down a bit since it was half its current age. That's not just background noise, that's exactly the kind of subtle slowdown predicted by Kaku's dark fluid theory. Now, it's far too early to rewrite the textbooks. This could still be a glitch, maybe a data bias, a calibration error, or just statistical noise, but even a hint of something off sends shockwaves through the astrophysics community. Researchers are now triple-checking everything, running simulations and poring over the data to see if this signal holds up. And remember, this is just the beginning. The next massive data drop is coming in 2026, expanding Euclid's sky coverage by 10 times. That's like going from a Polaroid snapshot to a full-blown 4K time-lapse of the universe across billions of years. Euclid isn't going it alone. In fact, it's just the first member of a cosmic dream team. In 2027, the Vera C. Rubin Observatory will come online in Chile. It's like Euclid's ground-based cousin, scanning the southern sky with wide-angle precision every few nights. Then, in 2028, NASA launches the Nancy Grace Roman Space Telescope, a dark energy specialist armed with cutting-edge infrared tech. Together, these three observatories will form a kind of galactic truth squad. They'll cross-check results, eliminate instrument bias, and tighten the error margins so much that theories either stand strong or collapse under pressure. By 2030, cosmologists expect to reduce uncertainty in the dark sector by a factor of 10. That's the kind of clarity that could finally reveal what the universe is truly made of. All of this points us toward three possible futures, each one more dramatic than the last. First, the dark fluid theory takes the crown. Euclid's data lines up with Kaku's predictions, revealing a single exotic substance driving both cosmic clumping and expansion. A new scalar particle, maybe the mysterious X boson, is proposed. And physics takes a giant leap forward. Classrooms around the world update their textbooks to reflect a universe ruled not by two opposing forces, but by one elegant unifying fluid. It's a scientific mic drop. Second, the reigning champion, LCDM, holds firm. Dark matter stays a particulate enigma. Dark energy keeps pushing the cosmos apart, with constant force. No grand unification, just a clearer, sharper understanding of what we've already built. It's not as flashy, but it's a massive win for precision science. Cosmology gains its most accurate ruler yet for measuring the shape, scale, and fate of the universe. And third, the wild card. The data matches neither model. Something deeper is at play. Maybe Einstein's general relativity needs a quantum makeover. Maybe there are hidden dimensions, or a fifth fundamental force that's been hiding in plain sight. In this version of the future, Euclid isn't the telescope that proved a theory. It's the one that shattered our old ideas and sparked a new age of cosmic discovery. Unraveling the secrets from Euclid's 6-year cosmic scan won't be a weekend project. It'll take supercomputers running non-stop, churning through trillions of simulations, matching theory to data pixel by pixel. Across the globe, teams of cosmologists, statisticians, and data scientists are already knee-deep, dedicating entire chapters of their careers to this mission. Because the stakes? They're sky-high. A single pattern hidden in Euclid's vast archive could rewrite physics. The next Nobel Prize might be coded into these light maps. And just maybe, this will be the moment when Michio Kaku's once radical idea steps out of the theoretical shadows and into the spotlight of mainstream science. The same way Einstein stunned the world by bending starlight, or Hubble forever changed our view of the universe, Euclid might mark the start of a brand new cosmic era. Euclid has only just blinked open, and already it's poking holes in the fabric of what we thought we knew. Will Kaku's dark fluid rise to rewrite the textbooks or dissolve into the cosmic background? We're on the brink of a breakthrough that could stand alongside the most monumental discoveries in the history of science. So, tap that like button, drop your wildest dark matter theory in the comments below, and don't forget to subscribe so you're the first to know when Euclid's next cosmic postcard arrives.